This is where we left off, and what we're going to do today, we are going to learn some new concepts, but the processes that we're going to be doing today are the same ones you've been doing, just applied in a different setting. Okay? And if you look at the problems that we've done so far in this chapter, most of them ask you to calculate a pH. The pH is the ultimate goal. Sometimes you will be asked not to calculate a pH, but something that's called percent dissociation. Sometimes you'll see it as percent ionization. And all that is a percentage, a number, indicating how much of that original acid has dissociated into its ions. What do you think that percentage would be for a strong acid? 100%. Okay? You're never going to be asked to calculate that because that's assumed. If we're talking about a strong acid, a percent dissociation would be 100%. Weak acids or weak bases, you could do it for bases as well, much less than 100. Okay? This is how you calculate it. Okay? This looks a lot wordier than it really needs to be. If you look at the weak acid problems that we did last class, okay, if you look underneath the ice tables, you should see that you ultimately found a value for X. X was that intersection point on the graph. Okay? Percent dissociation, what's in the numerator here, amount dissociated, is whatever you found X to be equal to. Okay. So you go in your calculator, you graph it, you find the intersection, whatever X comes out to be, that's what you put in the numerator. And what's in the denominator is exactly what it sounds like. It's the concentration that you were given at the very beginning of the problem. Go back and look at all the problems we've done so far, you're always given some initial molarity. Divide these, multiply times 100, that gives you a percent dissociation, or percent ionization. Now, I don't want to talk about these two statements until we have done a practice problem with this. So, we're going to do that. I'm going to give you a chance to do a little bit of review. Okay? I want us to look at this first problem. It says calculate the percent dissociation of a 1 molar and a 0.1 molar acetic acid. The word solution should be there. Okay? And then I give you a Ka value. It's a weak acid. You must have a Ka value. What I would like for you to do is, and please don't cross it out on your slides, but just for the moment, let's ignore this number and just focus in on this one. That is our initial molarity. Okay? And since it's a weak acid, we're going to set up an ice chart just like we usually do. I just want to give you a little bit of a head start, and then you're going to finish it. I want you to know that acetic acid is a weak acid that is used a lot on the AP exam. So frequently that there is an abbreviation for it that is perfectly acceptable on the AP exam. You don't have to write out acetic acid in its full formula. If you don't want, you can write that, and that's okay. You're going to use acetic acid a lot, so I'm showing you a little shortcut. But just to get you started, you're going to react it with water, just like we have been doing. What is one of my products going to be here? Okay, the acetate ion, I'm just going to write it as AC minus. And what's the other product? Hydronium. Okay, what I want you guys to do is take it from here. Set up your ice table. If you need to look at your notes from last class, please do. Get your calculators out. find X and stop there. Did you get that for X? Okay, well they're asking us to calculate a percent dissociation. So, to do that, I'm simply going to take that value for X that I just found, divide by my original concentration up here, my initial, times 100, and that's what I get. Okay. Now, I want you to understand conceptually what that number represents. That means, out of my entire acid sample from the beginning, only 0.42% of it broke apart. Is that a big number? Not at all. Okay, guys, when I say the difference between a strong acid and a weak acid is a big difference, that's what I'm talking about. A strong acid dissociates 100%. A weak acid, much, much, much less. That means 99.58% is staying together as acetic acid and is not breaking apart. Now, what I want us to do, let me scroll back up. I'm now going to unerase this. Okay? We're not going to have to go through and totally repeat this problem. I do want us to get a percent dissociation, same acid, same Ka value. The only difference is that initial molarity. All you have to do is go back into your calculator, into one of your Y1 or Y2, depending on where you put it. Go back and change what you had as 1.00 and put it in as 0.10 and tell me what X comes out to be this time. Anybody got it? 3 sounds right? Okay.
No, listen, it's something like what?
Let's calculate a new percent dissociation. X over the original concentration, which wasn't 1 anymore, but 0.1. And you get something like that. Now, if you have the slides, on the previous slide there were statements just below where it showed you how to calculate a percent dissociation. Now that we have a problem in front of us, I want to read the statement to you, okay? Just listen and look at the numbers as I say this statement. It says, for a weak acid, percent dissociation increases as an acid becomes more dilute. Okay, let me say it again. For a weak acid, your percent dissociation will increase as the concentration of that acid becomes more dilute. Okay? That might seem backwards, and I'll be honest, it seems a little bit backwards to me too. Because you think the more dilute it is, wouldn't that mean, less is breaking apart? Actually, it means percentage-wise, a greater percentage is breaking apart. Now, what I want you to do now, this is a very AP exam kind of question, okay? Because let's read it together. It says, what is the Ka of a weak acid? Meaning, I'm not giving it to you. What is the Ka of a weak acid that's 8.1% dissociated as 0.1 molar solution? This is taking the concept of percent dissociation and rearranging it a little bit. Okay? My suggestion to you on getting started, okay, we don't know what acid it is, so let's call it HA. Write out your reactions, set up an ice table. You will see that when you get down to the end, you'll be missing some information, but there's ways to get it. Try it. So this is a very, very AP exam kind of question because it takes the concept of percent dissociation and sort of rearranges it a little bit. You'll find in your problem set that you'll come across probably towards the end of the problem set problems where they've given you every piece of information you need except the initial molarity. And you have to work backwards, okay? They're very big on that kind of thing. If you stay organized and write everything out, because a lot of people last class were saying, do we really have to keep writing all this out?
Yeah.
Well, as you're taking notes, no, I can't force you to do that. But let me tell you that very soon these reactions are going to get more complicated. These are not going to be zero anymore. Okay? So it's in your best interest to keep writing it out.
So much better.
Okay, let's move on. Folks, we are temporarily leaving the world of acids and going into the realm of bases. Please do not think, oh, am I going to have to learn a whole new set of procedures? No, you're not. There will be some differences, but the processes are the same. So let's talk bases. Guys, you can use the terms strong and weak in the same ways that you did for acids. Okay? Strong still means complete dissociation. And just to refresh your memory on what are your strong bases, your group 1 hydroxides, meaning any metal from group 1 joined to hydroxide, and Cabasser. Okay? Those are your strong bases. Anything that's not in that list is considered a weak base. Okay? And instead of Ka, Now we'll have KB, B for base. Okay? It's not anything different, people. It's still just products over reactants. The only reason that B is there is because this is a base reaction. So don't get nervous about all these K values. They're all the same thing. Now, weak bases, same kind of concept as weak acids. That means very, very little dissociation. Okay? Most of your weak bases do not even contain hydroxide at all. Okay? Like ammonia is a great example we'll use a lot. NH3, that's a weak base, does not have hydroxide in it. Okay? Just to refresh your memory, base means proton acceptor, hydrogen ion acceptor. Okay? And here is an example. I want you to look at this compound. I want you to know that if you were seeing this compound for the first time, I would not expect you to look at it and say, oh yeah, that's definitely a base. Okay? If you didn't have this equation, if I just gave you that, I would not expect you to know that that is a base. How am I going to tell you? One of two ways. Same goes for the AP exam. They will either say the following weak base, comma, pretty clear, right? Or if they don't say that, maybe right after this compound is written in the problem, immediately after it, they give you a KB value. That's another clue. Okay, but just look at what's going on here. This base is accepting a hydrogen. Where did that hydrogen come from?
H2O.
The H2O. Okay, same kind of reaction. Water is still a reactant, but our products are a little bit different than in our acid equations. Okay, the name of this compound, you don't need to memorize it, but this is what it is. It's called methylamine, and I'm giving you a KB value. Okay, we're going to do this one together because the beginning of this problem is very much the same thing we have been doing, but the end changes things just a little bit. So what I want you to do, okay, is set up your ice table, okay, and then I'm going to do this right along with you, and then we'll see that the end is where things get a little different. Now, if this were a weak acid problem, and if you want to flip back to the ones we did last class, when we got to this point and the question said calculate a pH, what we had with X was also, whatever the value was, also was the concentration of H3O+, which is the same thing as H+. Look back, all we did was say negative log of whatever we got for X, and that was the pH. You can't do that here. Because, and you don't have to memorize this, if you've written out your ice table, the answer is there for you. What is X? It's not H+. It's OH-. Okay. So, unlike our acid problems, whatever X comes out to be is not our hydronium concentration. It is not our H plus concentration. It is our hydroxide concentration. Okay? But, can I get the pH from here? Yeah, what's probably the easier thing to find first?
POH.
Okay, pOH. Negative log 0.042. Okay, how do you go from a pOH to a pH?
14 minus 1.
14 minus your pOH. So here is our final answer. Do you know what I'm going to ask you? Nope. Does it make sense?
Yes.
Okay.
Basic solution.
What was it? It was a base. Our final pH should be somewhere between 7 and 14. Again, don't worry about where it is in that range. Is it in the basic range? Yes. We're good. Okay? Now, before I have you do some problems on your own, I want to introduce you to one of my little acronyms. And if you say this word to anybody from previous years, they'll be like, oh, wow, yeah, I know what that is. Okay, because it comes from this chapters 14 and 15. I have a little acronym that I use. I'm going to teach it to you, and I'm going to use this word from now on. I call these problems WOMIX problems. Not woman's problems. WOMIX. What do these letters stand for? W stands for water, because water is one of our reactants. What kind of numbers are we putting into these ice tables? What are these? Molarities. Run out of room. And we are adding and subtracting x's. Okay? All the problems we did last class, any of these ice tables we've done today, I call them WOMIX problems. Now, why am I coming up with an acronym? Because when we get into chapter 15, there's a new type, which has another acronym that I just made up. And so by the time we get to the getting ready for the test, you're going to be using what sound like ridiculous words. But it's all going to make sense to you. And no one else is going to know what you're talking about. Okay? It's like our own little secret language. Okay? So, what I want you to do, I want you to try these on your own. Before you start reading or calculating or anything, let me just say one thing. If you have a weak base, just like you had when you had a weak acid, it's a WOMIX problem. It's an ice table problem. Did we use ice tables for our strong acids last class? Did we do that?
No.
No. That means you don't need to do that for strong bases either. Intriguing. I want you to try these. With what we've done today, 2 and 3 will probably not be any kind of an issue. But technically speaking, number 1 is a very simple problem. Try it. I want to scroll up to number 1. I want to call your attention to something that you will see on the problem set. Okay? In number 1, alright, do you agree that potassium hydroxide is a strong base?
Yes.
Okay, good. When we had strong acid problems, remember that what made strong acid problems so quick and easy was because whatever the initial molarity given to you was also the molarity of H+, and you could just say negative log of that number, and find your pH and be done. No ice tables, no nothing. The same thing works for bases. The molarity of the whole, let me rephrase that. The same thing works for strong bases. The molarity of the whole thing is equal to the molarity of hydroxide ion. That is why I didn't have to do any more math than this. From the pH, I went to the pOH, found the hydroxide ion concentration, and that was my answer right there. However, what if the strong base given to me in this problem was not KOH? What? No. What if it was, hold on. This one. It's still a strong base, right? Okay, that means I don't need an ice table, I don't need any of that. But that too plays a role here. Okay, let's keep all the other numbers the same. This first line of my calculations would be unchanged, exactly the same. And hydroxide ion would still be 3.2 times 10 to the negative 4th. But the molarity of the entire thing, if it were calcium hydroxide, would not be the same number. Let me just bring this down here. And I'm going to set it up just like a quick little T-chart. If this is my molarity of OH minus, but that's not what I'm being asked for. I'm being asked for the entire compound. For every one of my entire compound, how many hydroxides are there? 2. That was not the case for KOH. I didn't have to do this because these numbers would just be 1 and 1. So if this problem gave you calcium hydroxide, what would you do to this number to get your final answer?
Divide by 2.
Divide it by 2. Be aware of that. Okay, we don't usually have to deal with this so much with acids, although we are going to do something with this next class. But with bases, 3 of your strong bases have OH and a subscript of 2, so you have to be careful with that. Okay? That is where I'm going to stop.